Welcome back to ECE 501B. As way of announcement, homework 5 will be arriving at D2L shortly. That's the plan. It's not there yet if you're anxiously looking for it. What I want to do is remind ourselves where we were when we stopped. We just had our first exam, so now we're coming back. We're starting again in Chapter 5. Hopefully we will finish Chapter 5, maybe not this time, but with the next lecture. We'll look then at eigenvalues and eigenvectors just to try to get us thinking about what that is again. And we'll start looking at some results with eigenvalues and eigenvectors through the different theorems and corollaries and propositions. One is, once you have distinct eigenvalues, if you find their corresponding eigenvectors, those are linearly independent, those columns or those vectors. That's theorem 5.6. You can only have the possibility of having distinct eigenvalues up to the dimension of your space, vector space that you're working on, which is, let's say, of dimension V. That's corollary 5.9. Then for every finite dimensional complex vector space, that's the FDCVS, of a non-zero dimension, you can have an eigenvalue. That's not true for real vector spaces, but for complex vector spaces, that is true. That's theorem 5.10. And then we'll get into some results dealing with upper triangular matrices and that special structure. And then we'll specialize that to diagonal matrices. But that's one way of thinking about operators, or a matrix representation of operators with respect to this material, eigenvalues and eigenvectors, and what this diagonal and triangular representation allows us to think about. Again, we're dealing with eigenvalues and eigenvectors. These eigenvectors are invariant subspaces. And those invariant subspaces are, well, they have nice properties. And essentially, if it exists, if you have an invariant subspace, let's say W, or a vector W, that when operated on by this linear map T, you stay in that same direction, then that's the eigenvalue-eigenvector relationship. TW is equal to lambda W. And you could rewrite that as this operator T minus lambda I times W is equal to 0. If lambda is an eigenvalue, then T minus lambda I is going to be non-invertible or injective, or not injective and not surjective. If it's not injective, it has a non-trivial null space, which means we can find this vector W in the null space of this T minus lambda I, and that will give us our eigenvector. Let's then start with that sort of recall of where we've been. Let's just start with a theorem. Theorem 5.6, and that tells us a little bit about the eigenvectors. The eigenvectors associated with or corresponding to distinct eigenvalues of some, let's say, linear map T, those eigenvectors are actually linearly independent. And we know what we can do with linearly independent vectors. We can start building up, let's say, a range space of a particular output vector space, which would be V, if that's our vector space of interest. So the eigenvectors associated with distinct eigenvalues of T are linearly independent. Let's look at the proof of this, just to sort of bring us back from a weekend. Suppose that we now have this linear operator and our vector space is V. And let's say that we have distinct eigenvalues. And corresponding to those m eigenvalues, let's just say that we have m eigenvectors. And what I would sort of have you make note of is that we haven't said that m was as big as the vector space that we're living on. In this case, m, the number of distinct eigenvalues, may not be the same number as the size of your vector space. That's what I'm calling n. So n is our dimension of V. So we don't have to necessarily have the full complement of distinct eigenvalues. M is some number less than or equal to n, where n is the size or the dimension of V. Once we have this, now what we want to do is prove that those eigenvectors are linearly independent. And the way that we will prove that is by contradiction. Meaning, let's go ahead and assume that those eigenvectors are linearly dependent. And then we need to find a contradiction. So now let's assume that these vectors, v1, v2, m of those, assume that set is linearly dependent. Now, once we have a set of linearly dependent vectors, you know what you can do with it. You can combine or create a representation of one of those in terms of the others. That's what we mean by, or that's one way of thinking of something being linearly dependent. So let's say then that we can now write that, or that means at least one of these vectors, v1 through v sub m, is in, let's say, the span of the other vectors. If that's the case, then let's let k be the smallest integer such that v sub k is in the span of all the previous vectors. And these are eigenvectors. So let's find the first k, or the smallest integer k, such that this is true. Now, if that's the case, we can write v sub k in terms of those k minus 1 vectors. I can't make k's to save my soul. Can I do this? How about these are now L's. Okay, so this is now v sub L is equal to a1 v1 plus a2 v2 on up to a sub L minus 1 v sub L minus 1. That's okay. by our assumption that V sub L is living or is in the span of these previous L minus 1 vectors. Let's now operate on both sides with T, the linear map. So if we now apply T to both sides of that expression, we end up with T V sub L is equal to A1T V1 plus up to A sub L minus 1 T V sub L minus 1. But all of those TVs are special, aren't they? Since the V's are eigenvectors, those TVs all can be written in the same direction of that respective V. So TV1 looks like lambda 1 V1. TV2 is lambda sub 2 V2, etc. Meaning we can now rewrite this as the following. We can say, and I'll call this lambda 1, we can now say that lambda L V sub L is equal to A1 lambda 1 V1 plus all the way down to A sub L minus 1 lambda sub L minus 1 V sub L minus 1. And that's because these T V sub I are eigenvalue eigenvector pairs. Now, we can also go back to this governing relationship for V sub L, and we could multiply that by a constant. Let's just make that constant our eigenvalue of interest. Let's make that lambda sub L. So now I can multiply this equation by a constant lambda sub L, which allows me then to, let's say, but since V sub L is equal to this A1 V1 plus A sub L minus 1 V sub L minus 1, I can now, multiplying by lambda sub L, say that that is now lambda sub L V sub L is equal to A1 lambda sub L V1 A sub L minus 1 lambda sub L V sub L minus 1. And what I want to do now is actually combine 1 and 2. I can now subtract, well, which one do I want to subtract? What do my notes say? How about I subtract 2 from 1? And then I have the same thing on the left-hand side. I'm going to end up with 0 on the left-hand side, but on the right-hand side, I'm going to have some interesting terms to look at. If I now combine 1 and 2, on the left I have 0, saying lambda sub L V sub L minus lambda sub L V sub L is 0. And on the right, I have A1 in common, but I have the difference between lambda sub 1 and lambda sub L. And the V1 is okay. That's the same. I now have A1 with lambda sub 1 minus lambda sub L V1 plus A sub 2 lambda sub 2 minus lambda sub L V sub 2, and let's say A sub L minus 1 lambda sub L minus 1, lambda minus lambda sub L, V sub L minus 1. Let's say that's equation 3 if we need to refer to it. But what do we know about the V1, V2, and V sub L minus 1? Do we know anything about that? So now from this assumption, with V sub L being the smallest integer before it belongs in the span of all the previous vectors, all of these vectors, V1, V2, and V sub L minus 1, must be independent. So if these guys are linearly independent, that tells us now something about what's happening down here. We have a linear combination of linearly independent vectors that are equal to 0. And that you should sort of start to think, what's going on here? What happens when we have a sum or a linear combination of linearly independent vectors equaling 0? What I've tried to say then is because those V's, V1 through V sub L, were linearly independent, and that was by our choice of V sub L, because V sub L was the first vector that could be written in terms of the earlier vectors. Or those earlier vectors are the V1, V2, V sub L minus 1. Then these V sub 1 through V sub L must be linearly independent. And that linear combination of linearly independent vectors is equal to 0. That means we could have a couple of things happening. Either have all the A's 0, or we could have something mixed up with these distinct eigenvalues. Therefore, because of 3, that actually implies all of the coefficients are 0, which that really is saying that we have I1 lambda 1 minus lambda sub L equaling 0, etc. And that says that either that lambda sub L is mixed up with all the others, or we don't have these distinct eigenvalues, or all of these A's are 0. So either there are non-distinct, which is really hard to do because we had so many of them. Well, unless we just had L equal to 1 or 2. Either there are non-distinct eigenvalues, which is a contradiction, which we're looking for contradiction since we're doing this proof by contradiction. We started out by assuming that set of vectors was linearly dependent, which is what we're actually trying to prove it is linearly independent, or all of those A sub j's are 0. Now, if all the A sub j's or the non-distinct eigenvalues cause that to equal to 0, what's that say about V sub L? Sub L was this A1, V1, A sub L minus 1, V sub L minus 1. If all the A's are 0, then V is 0. And that's a contradiction, since we assumed that all of these vectors were non-zero. And that behavior is true for all k. We just sort of grabbed a k, or we said, here's the first k. And that then says that all of these vectors corresponding to the m distinct eigenvalues, lambda sub I, this set of eigenvectors must be linearly independent. That's a pretty strong result, actually. You give me a matrix and give me the m distinct eigenvalues. Now, if I find the associated or corresponding eigenvectors for those eigenvalues, and that's a null space computation. If I have the matrix T, I do a T minus lambda sub ji, and then find the null space of that, and now I have an eigenvector. I get all of those m eigenvectors, and they're going to be linearly independent from this particular theorem. Yes? Which three? Must be linearly independent, because these, yes, so these vectors, v1, v2 through v sub l minus 1, since v sub l was the first vector to be in the span of these earlier ones, then none of these earlier ones were in the span of the previous. If that's the case, then these all, when you add another one, must be giving you a new direction. So all of these are linearly independent. Is that making sense? So v1 through v sub l minus 1, that set of vectors is linearly independent by design, by the choice of v sub l. We said v sub l was the first one to be in the span of all of these others. And that made v1 through v sub l linearly dependent in our original assumption. From that result, it's pretty quick to state, I'll just state it, I won't prove it, you can look in the book for the proof, but now for corollary 5.9. This says if we have a linear map, T, then that linear map cannot have any more than the dimension of V distinct eigenvalues. So if we had a four-dimensional space, we better not be saying we have 5 distinct eigenvalues. We can only have as many as 4. We may not have that many, but that's the best we could do as far as distinct eigenvalues are concerned. Now, to keep going, and one of the reasons why we are playing with operators. What's an operator? I guess you're too old to have called an operator on the phone, or too young, I should say, to have called an operator, but you used to have to talk to an operator on the telephone. Operator, can you call? And they'd put you through. They would connect you through. That was networking, right? But now we're talking about a linear operator. What's a linear operator? What's one of the key features of a linear operator? It goes from its domain back into its codomain is its domain. So it's mapping between itself, right? Now, that gives us a lot of power, or a little bit more interesting relationships, which allow us to deal with polynomials and then look at powers and polynomials or functions on these operators or with these operators. Since an operator is a map, a linear map, from a vector space into itself, then we can repeat those mappings without a problem. Repeated applications of this map are well defined. Meaning, if we now have T in this set of linear operators on V, we're going to define a couple of different concepts. T to the M is really just the same thing as multiplying T by itself M times. That's what we mean by T to the M. We just say T, T squared, T cubed. That's T times T times T times T times T. Up to Michigan times. Also, we define T to the 0 to just be the identity map. Just like x to the 0 or 4 to the 0. Something raised to the 0 power is 1 if we're dealing with a scalar. With a matrix now, that's between multidimensional vector spaces. That's now the identity map I. With this notation, we can now define polynomials as operators, or polynomials of operators. For example, if we had a polynomial of z as a sub 0 plus a1z plus dot dot dot, let's say a to the m, z to the m, now we can replace that z with this linear operator, t. Or p of t is now a sub 0, and this a sub 0 in our polynomial was scaled by z to the 0. It's not there, but it is implicitly. So now we have t to the 0, but we'll just rewrite that as the identity map, plus A1. So everywhere we see a Z, we replace it with T. T plus dot 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 plus A to the M T to the M. And now that we have these polynomials, we can start talking about generic functions of operators. And this is opening up a lot more possibilities. So once we have polynomials, we can even start talking about more general or more complicated functions of operators. So if we're given some function of, let's say, a variable z, then we can, if we can rewrite that generic function as a polynomial in z, or if we can make this a relationship, let me then say that we can replace that function, general function, with this polynomial function of t. And this p of t, or p of z, could be the Taylor series expansion of that function, f of z, where p of z is the Taylor series of f of z. For example, suppose that we're given t is this linear operator, and maybe our function f of z is this exponential, e to the z. Now we can find the matrix exponential. All we have to remember is the Taylor expansion of e to the z. You remember what that is? E to the z equals I'll start 1 plus z plus, and then we start using a lot of our fun symbols, right? Factorials, powers. So now we have 1 plus z squared over 2 factorial plus z cubed over 3 factorial, etc. That just keeps going. And now we can say that if we wanted this matrix exponential, e to the t, now that's going to be I plus t plus just a constant, 1 over 2 factorial times t squared, plus 1 over 3 factorial t cubed, etc. And this matrix exponential is used in a lot of things. Control for one, maybe quantum mechanics. It's used heavily in, let's say, advanced topics. Now, once we have that, it might be nice to be able to compute that in an easy way, and what we want to maybe do is start representing this operator in cleaner or simpler ways, the matrix representation of these operators. And we'll be doing that in ways that try to utilize the eigenvalues of that matrix and the eigenvectors. Which it would be nice to know, when do we actually have eigenvalues for an operator. And that's what theorem 510 tells us. It says that every operator on a finite dimensional and now you don't want to forget this next word, complex vector space, in contrast to real. I'm not saying this for real vector spaces. This is now for complex vector spaces. So a finite dimensional complex vector space, FDCVS, of a non-zero dimension, then that operator has an eigenvalue. Let's just convince ourselves that that's true. So now we're saying, if you give me an operator and we're living on a complex vector space, then that, if we're on a finite dimensional complex vector space, then that operator has an eigenvalue. We can find one. So now first we need to be assuming that we have this complex vector space. Given a complex vector space, let's call it V, and let's just assume that the dimension of that complex vector space is n, and we're assuming that n is bigger than 0. And now we have this operator T living in that complex, finite dimensional complex vector space. Once we have that, let's go ahead and choose a vector in that vector space. So let's choose a little v in our vector space, and let's assume that that's non-zero, that vector. Suppose I build the following list of vectors: T, TV, T squared V, on up to T to the n V. What do I know about that set or that list of vectors? And now I have to just sort of count what I have, or keep track of what I have. How big did I say capital V was as a vector space, as a complex vector space? I said its dimension was Nebraska, right? N. Don't want to go any further north, we'll get snow. Okay. 4 feet of snow. Wow. Glad I'm in Arizona. But we don't have Arizona vectors, we have Nebraska, right? N. So we have Nebraska vectors, or that's the dimension. How many vectors do we have here? So we have 1, 2, n. Ooh, we have an extra one, don't we? N plus 1. Now if we have a set of n plus 1 vectors in a Nebraska vector space, what do we know has to be true about those n plus 1 vectors? Can't be linearly independent, can they? They have to be linearly dependent. So we have one more vector than we can possibly have to have linear independence. So this list, the list v up to t to the nv, must be linearly dependent since we build it to be of length n plus 1, and our underlying complex vector space, capital V, we said was of dimension n. And now we can just play with what we've been playing with, and you've played with this on the exam, most of you, this notion of linear independence and what that means with respect to coefficients. Thus, if we write 0 is equal to, let's say, a sub 0 v plus a1 tv plus a to the n t to the n v, what do we know about some of those a's? If we know we have linear dependency among those n plus 1 columns, v through t to the nv, then some of those a's can be non-zero. We can find a set, and the a's, since we're dealing with v being a complex vector space, these a's may have to be complex. That's okay. A set of complex a sub l's not all 0, that make this equation true. Now what we want to do is sort of what we did with L before. We want to sort of find the first one, or maybe the biggest one here, that's not equal to 0. So of all of these, a0, a1, a sub n, maybe a sub n ends up being 0. Maybe a sub n minus 1 ends up 0. We want to go back and find the biggest one that's not 0. And we're going to call that Michigan, M. So let's now find, let M be the largest of those A coefficients So let m be the largest integer such that a sub m is not equal to 0. And now let's sort of look at what we have. We assumed at the beginning that this vector v that we started with in the complex vector space was non-zero. And we now know that this equation is true. And if v is non-zero, then a sub 0 either needs to be 0 if m was 0. So let's look at some of the possibilities. Either a sub 0 is equal to 0, or a sub 0 is not equal to 0, and some other a sub l's are not equal to 0. Which really just says that this m is bigger than 0, is what we're trying to say. So either a sub 0 is 0, or if it's not, then the little m is 1, 2, etc. but it's potentially less than n, Nebraska. Now what we want to do is use these polynomials in this expression to write a polynomial. So we have these a's, a0, a1, that allow this to be true for the v and the operator t with the different powers. So now let's go back and say, I kind of like these a's. Let me build a polynomial from those, where now that polynomial will be a sub 0 z to the 0 plus a1 z to the 1, etc. So now that I have this possibility, we can use the a sub l's to build up or to write a polynomial. And let's just make that polynomial a function of a complex variable z. P of z is now this a sub 0 plus a1z plus a sub 2 z squared all the way up to a sub n z to the n. Now, we didn't dig much into Chapter 4, but now I'm going to go back and recall what we learned from Chapter 4, or what we are drawing from Chapter 4 about polynomials. What do we know about any polynomials of finite order in Z, where Z is complex, or this complex field? We now, let's say, any polynomial of order n with potentially complex coefficients has how many roots? So now if I had a third order polynomial, how many complex roots would that have? 3. So this is going to have Nebraska complex roots. And once we have those identified, we can factor that into these linear factors with the complex roots. So now we have n complex roots and can be factored into these n linear terms. Now this is definitely not true for for real coefficients or for the real field. So this is not true. I guess I'm putting it in red, sticking with the color theme of the university, red and blue. So that's not true for real polynomials in general. And we'll get back to that. But there we had to have quadratic factors, or potentially quadratic factors, that couldn't be factored into real linear factors. But once we have these n terms, then we can rewrite P of z, this polynomial, this nth order polynomial, is some, let's say, complex number, z minus lambda 1, z minus lambda sub 2, up to z minus lambda sub n. So this is really just an order m polynomial. So that's what we're assuming is true. Now that we have that polynomial and factored it, now we can go back and play with our operator equation. If we go back to the polynomial in t, then we have 0 is equal to a sub 0 v plus a1 tv plus a sub 2 t squared v squared plus all the way up to a sub n t to the n v. So I don't want to do a v squared, do I? I just want v by itself because I want to factor it out. That's just my vector, my non-zero vector. Now, once I have this, I can start playing with additivity, homogeneity if I want to. Via additivity, I can factor out that vector v. That's what I want to do, and just isolate the polynomial in t, essentially. So now I have 0 is equal to a sub 0, and now let me put this I in there. I guess I wouldn't have to, but I'll go ahead and do it now. A sub 0 I plus a1t plus a sub 2 t squared all the way up to a sub n t to the n times v. But this that's this polynomial in t, where we were saying it could be this polynomial in z. And what do we do now? Now we can factor this in terms of linear factors in t. And that now says that we have 0 is equal to c times t minus lambda 1I, t minus lambda sub 2I, etc., where I'm putting in these identity matrices to make it consistent. Otherwise, I would have a matrix minus a scalar, and that doesn't make sense. But this is now up to t minus lambda sub m I v. That right-hand side now is equal to 0. Can we say anything about what's happening on the right-hand side? You could think of those as, let's say, matrices. And now I have these matrices, and these actually commute. If I want to, I could slide these around and not mess anything up. And I could slide t minus lambda sub I over here next to v. But I know something is collapsing, isn't it? If this is equal to 0 in this collection of terms. This now means that if I look at t minus, let's say, lambda sub j I v, for those it maps to 0, doesn't it? At least one. But what does that mean? That means for at least one of these lambda sub j's, this t minus lambda sub I, or lambda sub ji, has a non-trivial null space, which means that this gives us our eigenvalue eigenvector equation. TV is equal to lambda sub JV for some J. That's what we want. We wanted an eigenvalue, if you remember where we even started. We were trying to show that for a linear operator on a finite dimensional complex vector space, we could get an eigenvalue, and that's what we've now just shown. This now says that T has at least one eigenvalue. And I think that was theorem 10, wasn't it, in chapter 5? Now this will really test my memory. Wow, really? So that was theorem 10, 510. Now we know that if we have these, and what did I say before 510 started? I said it might be nice to be able to manipulate these operators quickly or with nicer representations, matrix representations. That was one of our goals. And now we know that if we have these operators on a finite dimensional complex vector space, we can find an eigenvalue for that operator. And once we have that, then we can start making things a little easier. And one way we can start making things easier is if T, if you think of it as a matrix, as a big matrix, maybe all of these terms are not all non-zero. Maybe we have a lot of zeros in them. And a nice operator or a simpler operator might just have all zeros below the diagonal. That might be a nice operator or a simple operator. And that's where we want to look now. Let's now look at what are called upper triangular matrices. And what's nice is the representation is not so critical. It's the underlying functionality that's happening. And if we can represent it by an upper triangular matrix, that'll maybe save us some or give us a little bit more insight or provide us with an easier way to compute something. But we're not destroying any of the physical behavior or the operating properties of these maps by switching to or representing things via these simpler matrices. So upper triangular matrices, if we just jot down some quick notes on our matrix representations, if we're dealing with an operator, what kind of a matrix do you immediately see in terms of a geometric shape? A square, right? So now if we're dealing with operators, we're dealing with square matrices. And if we're going from one vector space back to that vector space, we don't need to mess with two different bases. We can just work with one. So we only need, let's say, to specify one basis. We're actually looking to find good, or maybe what somebody else might consider efficient, basis for these systems that we're dealing with, or for these linear maps, for the operators. I'll just sort of say system because that's maybe what we're doing. We're mapping things. signals with systems, and these operators now are representing systems behavior. Once we say we want a good or efficient basis, what in the world does that mean? Well, here's the claim. We're going to claim that a good basis is one where the matrix representation of our operator is simple. Boy, I'm using a lot of quotes, aren't I? Good, efficient, simple. What am I meaning by all of this? Simple maybe means lots of zeros. So now what we want to do is see if we can build up operators that have quite a few zeros in them. And that's where this upper triangular and diagonal matrices are going to come from. The results that we've already played with or developed those are actually sufficient to show that for a finite dimensional complex vector space, there is a basis where the representation of our linear operator t, and I guess the notation that we've been using is this matrix representation of the linear operator t is actually some lambda. That's the only non-zero entry in that first column, and then everything else, who knows what it looks like, where this is arbitrary. Where did that come from? How can we show that the matrix representation of our linear operator t looks like a column of zeros except at the very top entry is some scalar lambda? How can we make that claim? Theorem 510 just said we can find an eigenvalue for a linear operator. So we know that we can have this relationship. Let's say AV is equal to lambda V, where A is our matrix. So now we have this V. If we sort of make that our basis vector, then we can say, oh, in terms of that basis, I can just multiply that basis vector by lambda in the expansion of a set of basis vectors, and that's now my representation of that operator, let's say A, in that basis. We've played with that before. That's what I'm going to try to sort of state in this proof. So the first step is that we've previously proved, really we just did, that T has at least one eigenvalue, lambda, and a corresponding or an associated eigenvector, let's say V. So now we have one vector V living in the complex finite dimensional vector space capital V that's maybe n-dimensional. And if we need a set of basis vectors, we know how to, or we know a result that if I give you one vector, you can extend to complete the basis, can't you? You know that that a set of vectors, a set of linearly independent vectors, can be expanded to fill the whole space. And that's what we're going to do now. We know that we have at least one eigenvector. Well, we can expand from that one to fill up the entire vector space. And we know what the relationship is with respect to V. That's an eigenvalue-eigenvector relationship, and we can say that we can now show in a particular basis that we can move in or stay on that single eigenvector through that linear map. So number 2 says that we've already also, or previously, proved that we can take a vector and expand from that. Previously proved can always extend a linearly independent list of vectors into a basis. If that's the case, then we can extend from this single vector V to a basis on this finite dimensional complex vector space, V. And once we have that, then we know that the matrix representation of that linear map can be lambda in the first column. And what happens after that, who knows, because we've just extended the basis. We didn't restrict or create that in any special way. We just said extend the basis. But we do know, with respect to that particular first vector, that we can just say, oh, that's our first vector in our basis set, and now we just need to scale that by lambda in our linear operator, or matrix representation of this operator T. Now, once we have that, what I'm saying is, how did we build up or represent a linear combination of basis vectors? So remember the kth column of the representation is the result of applying T to the kth basis vector. And in this case, it's the first vector. So our first vector is actually going to be the eigenvector that we want, written in terms of a basis of our eigenvectors that we had, or that we found V. Our first vector is the eigenvector V, and how do I represent V in terms of this newly created set of basis vectors? Meaning I had, well, let me say that I had a V, then let me just say that I extended it with a W1 plus a W2 plus a W sub n minus 1. And I now need to build up V from this. So I really need to just be doing this, don't I? Or I need to be putting a 1 there. So in terms of those vectors, I have that for my representation. So these were the basis vectors. And we know that we had TV is equal to lambda V. For V is an eigenvector. And what we want to do is actually show, or maybe we'll just state, that we can keep doing this process, and keep building up combinations that only depend on previous eigenvectors in the relationship or in the representation that we want. So right now, all we've done is really we found that we could find a matrix representation where the first column is simple or nice, and now we want to extend that to where maybe the pieces on the diagonal are these non-zero eigenvectors, and everything else above it is kind of arbitrary, but everything below it is strictly zero. That's where we want to go. But we can do even better. And that's where we want to go. And that is an upper triangular matrix is one where all of the elements below the diagonal are zero. Meaning we want to find representations of these operators that are upper triangular, meaning we can have everything below the diagonal 0 and everything above is now what we want to play with. And that's where we want to go, and we'll derive or state some nice results for upper triangular matrices next time.